In this video, we will be solving linear systems of equations by graphing. A linear system of equations is two equations with two variables, and we're essentially finding the point where they intersect, or a point that satisfies both equations. In the example in front of us, we have two lines, and you can see that they intersect at the point 3, -2. So that would be the solution to the system of equations. That point 3, -2 satisfies both equations, and we can check to make sure that it is the solution by plugging the coordinates into both equations. If I plug that point into the top equation right here, so I'm plugging -2 in for y and 3 in for x, and it should end up equal on both sides. I get -6 plus 4 on the right side, and -2 does equal -2, so I've confirmed that the point 3, -2 satisfies the top equation. And if I check the bottom equation, -2 in for y, and I plug in 3 for x, and I simplify. 1/3 times 3 is 1, minus 3 is -2. So I've shown that point 3, -2 satisfies both equations and is the solution to the system of equations. Now, unfortunately, not all systems of equations have solutions. We call a consistent system a system of equations that has at least one solution. And it might have one solution or more. And then an inconsistent system is a system of equations that has no solution. Now, if we look at our consistent systems, there's two different types, an independent and a dependent system. An independent system has one solution. A dependent system has infinitely many solutions. Now, let's look at some examples to discuss how this could happen. If you have two intersecting lines, like this diagram on the left, that is one solution. It's a consistent system of equations because it has at least one solution, and it's independent because it has exactly one solution. And in this case, you have two different lines. And they have different slope. And in this case, in the diagrams shown, they also have different y-intercepts, but they could have the same y-intercept, but the key is that they have different slopes. The next diagram in the middle, coincident lines, is when you have two equations that are actually the same exact equation. So they represent the same exact line. If we graph that red line and a blue line on top of each other, it's showing a purple line because, of course, red and blue make purple. But we have, if you have the same line graphed on top of itself, what you get is infinitely many solutions because every single point on this line is going to be a solution to that system of equations. Our independent system only had one solution. The two lines with different slope only touched at one point. But if you graph the same line on top of itself, it will have an infinite number of points that are solutions. So we say infinitely many solutions. It's still a consistent system because it has at least one solution. It has a lot more than one. And we call that dependent because it has infinitely many solutions. So in the case with coincident lines, you have two lines that are exactly the same. So they're going to have the same slope and also the same y-intercept. And then our third case, parallel lines, is two lines that never touch. Two lines that don't intersect or parallel lines will always have the same slope, but they are two different lines, so they're going to have different y-intercepts. And we call that no solution. It has no solution because the lines never touch. They have no point of intersection. And we also call it an inconsistent system because that is the word we're going to use for no solution. Here's an example of solving a system of equations by graphing. I'm going to take my first line here. We have two lines, 2x plus y equals 5 and negative x plus 3y equals negative 6. Neither of them is in slope-intercept form, so I think it might be easier if we put them both in slope-intercept form because that's a nice form for graphing. So I'm going to take 2x plus y equals 5 and solve for y. And to do that, I just need to subtract the 2x from both sides so that term moves over to the other side and I get y equals negative 2x plus 5. Now I'm going to do the same thing with the other equation, negative x plus 3y equals negative 6. I'm going to solve for y, so I'm going to add the x to both sides to move that term over to the other side. And then I'm going to divide both sides by 3 to isolate y. And I get y equals 1/3 x minus 2. And now I'm going to graph both these lines and find the point where they intersect. Y equals negative 2x plus 5 has a y-intercept at 5. The slope is negative 2 over 1. So I'm going to go down 2 over 1, down 2 over 1, down 2 over 1, and make a bunch of points on my graph. And then I could also go up to left 1, and make a few more. So there's my first line. And now I'm going to graph my other line. I'll use a green one for this one. So actually this form, in slope-intercept form, our y-intercept is negative 2. The slope is 1/3. So I go up 1, right 3. And I actually landed on one of the dots. I can make a few more points if I want. But I already landed on the dot where they intersect. So I make a few points on each line so I can clearly show both lines, but I found right here at this point, positive 3, negative 1, that is their point of intersection or the solution to this system of equations. And you should always check to make sure your solution satisfies both equations. And I would check in their original form just in case you made a mistake somewhere along the way. So I'm going to check first 2x plus y equals 5. I'm going to make sure 3, negative 1 satisfies that equation. So I plug 3 in for x, negative 1 in for y, and I hope that this works, and it does. I get 5 equals 5, so that point did satisfy that equation. And I also want to make sure it satisfies the other equation, negative x plus 3y equals negative 6. So I plug 3 in for x. I get negative 3 plus 3 times negative 1. And I hope that it equals negative 6. I simplify the left-hand side. Negative 3 minus 3. And I do get negative 6 on both sides. So I've confirmed that that point does satisfy both of those equations, and it is the solution to my system of equations. This equation had one solution. It was consistent, which means it has one or more solutions, but since it had exactly one, it's an independent system of equations that has exactly one solution. And it had exactly one solution because we had two different lines with different slopes, and they had a point of intersection. Here's another example similar to the one we just did, but I want you to try it on your own. So pause the video. You can write it down and give it a shot on your own, and then I will just show the solution. So go ahead and pause. Hopefully you took the time to solve that on your own, and here you can check your answer. The top equation was already in slope-intercept form, so I converted the bottom equation to slope-intercept form. I graphed them both. I found they intersected at the point -2, -3. I checked to make sure that point satisfied both equations, and it did. So this was another system of equations that was independent. It's independent, meaning it has one solution, and that's because we have two lines with different slopes. Now we're going to look at an equation, a system of equations where something a little strange happens. So if we take that top equation and solve for y, 8 equals 4y plus x, I'm going to subtract the x from both sides to move that over, and I get negative x plus 8 equals 4y, and now I'm going to divide both sides by 4, and I get -1/4 x plus 2 equals y. And if I graph that line, I have, this is the same as y equals -1/4 x plus 2 if we want to write it so it looks like y equals mx plus b. My y-intercept is at +2, and my slope is -1/4. So down 1, write 4. And I make a few dots and graph my line. And now if I graph the other line, it's actually exactly the same equation. So if I plot it, it's going to also have a y-intercept of 2 and a slope of -1/4. So the second line is landing right on top of my first line. We call this a dependent system. And it has infinitely many solutions. Every single point that is on those lines is a solution to the system of equations, and it has an infinite number of points on the line. I could keep drawing more points on this line all day. It's actually the same exact line on top of itself, and it intersects at an infinite number of points. We also call these coincident lines. And it's two lines that have the same slope and also the same y-intercept. So they're exactly the same line. Here's one last example where something slightly strange happens. So the first equation is already in slope-intercept form. I'm going to solve for y in the second equation. I'm going to subtract 4x from both sides, and I get 6y equals -4x plus 18. Divide both sides by 6. Y equals -2/3. I'm reducing 4 over 6. X plus 3. And so I graph that line. We have a y-intercept at 3, a slope of -2/3, down 2, right 3, down 2, right 3, or up to left 3. And there's some points on that line. And now I'm going to graph the other line, the top one, and it's already in slope-intercept form. Its y-intercept is -1, but slope is also -2/3, down 2, right 3, down 2, right 3, and there we have two parallel lines. And we know these lines are parallel because they have the same slope. And these lines will never intersect, so that is no solution. This is an inconsistent system of equations. It's two parallel lines that never intersect. And notice these lines had the same slope, but they had different y-intercepts. In this last part, we are going to talk about how to determine what type of solutions a linear system will have without even graphing, to classify them as independent, dependent, or inconsistent. And all we need to do is put the two equations in an equivalent form. And I would say it's easiest to put them both in slope-intercept form. If you find that you have two lines with different slope, it's going to be two intersecting lines. And it will be a consistent system of equations, and we would also call it independent because there's exactly one solution. If you put your two equations in an equivalent form and you find that they're the exact same line, that's going to be coinciding lines, infinitely many solutions. So in this case, you're going to find that the lines have the same slope and also the same y-intercept. And the third case is if you put them in equivalent forms and you find that they have the same slope but different y-intercepts, that's going to be two parallel lines. Same slope, different y-intercepts. So what I would like for you to do now is pause the video and try A, B, and C. Put all of the equations in slope-intercept form, so solve for y in all of those equations, and then compare the forms and determine if they are independent, dependent, or inconsistent. Okay, hopefully you paused the video and tried these on your own, but here's the solution. So in part A, when I solved for y in both equations, I found that they had the same slope but different y-intercepts. Those are two parallel lines, and that's an inconsistent solution. In part B, when I solved for y in both equations, I had two lines with different slope. And if the slopes are different, then those two lines will intersect. There will be one solution, and that's an independent system of equations. And then in part C, I solved for y in both, and I found that the two lines were exactly the same. Same slope, same y-intercept. That's a dependent system of equations, and it has infinitely many solutions.